Alright, welcome everybody. So today I'm going to tell you about the laws, and the laws that we're going to talk about are as follows. The first one is going to be Boyles Law, and Boyles Law describes the relationship between pressure and volume. And it looks like this: pressure times volume is equal to a constant. Or if you're looking at two conditions, P1 times V1 equals P2 times V2. And that is the relationship between pressure and volume. And so when I have the graph of this and I graph pressure versus volume, the graph will be inverse. And it will not be a linear graph, it'll be an exponential change. When I look at volume versus temperature, that's called Charles's law. And Charles's law, the temperature has to be in Kelvin, it's the absolute temperature scale. And when I look at volume versus temperature, I have volume, and I have the relationship like this, which is direct. In the same way that I had pressure times volume equals a constant, volume over temperature equals a constant, or we could do V1 over T1 equals V2 over T2. The third law is Gay-Lussac's law. So Gay-Lussac's law is pressure versus temperature, and that equals a constant. And the same way I could do conditions, temperature 1 equals pressure 2, temperature 2, and the relationship will be again direct, where we have pressure versus temperature. Finally, I have volume versus moles of a gas equals a constant, and this is Avogadro's law. And with Avogadro's law, again, we could have, V over N for moles in condition 1 equals V2 over N2 for moles, again, where we could graph moles versus volume and have a direct relationship. So all of these are direct except for Boyle's, which is inverse and exponential. Please memorize the names of each of the laws and what each of the laws look like. Okay. Here's a graph of Charles's law, and this is showing you that if we extrapolate the points where we graph temperature versus volume, what we'll see is that by extrapolating the graph back to the origin, we reach a certain point where the temperature is the lowest possible temperature imaginable, minus 273 Kelvin, which is also known as 0 Kelvin. So negative 273 degrees Celsius is 0 Kelvin. This is called absolute zero. This is the coldest temperature that is possible. We've never actually reached this temperature. We've come close, but we've never actually reached absolute zero as of yet. Now what's nice is that we can combine all of these laws together into a combined gas law. And that combined gas law, if we have constant moles, we will have pressure 1, volume 1 over temperature 1 equals pressure 2, volume 2 over temperature 2. If we include moles and vary that, we have P1, V1, N1, T1 equals P2, V2, N2, T2. Now, some things that you have to be clear about. Pressure, it could be any of the pressure units as long as you keep them constant between pressure 1 and pressure 2. Temperature has to be in Kelvin. So temperature must equal Kelvin. Moles have to be in moles. Volume could be milliliters, liters, but temperature must be in Kelvin. If it's in Celsius or Fahrenheit, you have to convert it. Okay, here's an animation. It's worthwhile to take this URL and type it into your computer and look at it. You need Java in order to get this to work. But if you have Java, you can get this to actually work, and then you could see the animation by changing all of the conditions, pressure, volume, moles, temperature. You can see how the gas will behave differently. What's cool about this one is they have one gas that's colored red. That one particle is nice to keep an eye on. And because you can see that, sometimes it slows down, it has those elastic collisions, it has those inelastic collisions, And so that's really important. You can sort of see how it interacts and how it works. So try out that website. You need Java to make it work, but it's well worthwhile to look at. Okay, so let's look at a gas law problem and how we would work with this. So when I look at this, I would start with my gas law, P1, V1, N1, T1 equals P2, V2, N2, T2. And now I would plug in my values. So it says that an ideal gas contains 24.8 milliliters. That's my V1, that's a volume. At 1.12 atmospheres, that's my P1, that's my pressure. By applying the plunger, the pressure is increased to 2.64, that's P2. Assuming constant temperature, find the new volume, V2. Now I look at this and I say, well, I have my combined gas law, but what I notice is that they say that I have constant temperature. And they say that it's in a syringe. That means that it's probably a closed container because they don't mention anything about moles. So before I start trying to plug in all of these values for temperature and moles, which I don't know, I can make them up, I ignore them. It will make life much easier if I just do Boyles, P1 V1 equals P2 V2. So now I can plug in my values. I have 1.12 ATM times 24.8 milliliters equals 2.64 ATM times V2, or X, and I can solve for X. So you can see that, if I have these numbers, if I'm given things that are constant, I can leave them out. Now, the second problem over here, they're talking about 5 liters at STP. And then they say, what will the volume be at 0.2 atmospheres and 100 degrees Celsius? And so this one has more difficulty to it. First of all, at first glance, it looks like you're missing values. But it turns out that they gave you a P1, a V1, and a T1. They just hid the P1 and the T1 in this term right here. This is T1, standard temperature, 273 Kelvin. And this is P1, we'll leave it in atmospheres since the second pressure is at atmospheres, and so that would be 1 atm. Also be careful because in this one, the temperature, 100 degrees Celsius, you should make it into Kelvin, so that's 373 Kelvin. If you don't know how I did that, remember that Kelvin is equal to degrees Celsius plus 273. And if you have Fahrenheit, Fahrenheit is equal to 1.8 times degrees Celsius plus 32. So here are all my values. I can go and I could plug them in. I could solve, but I want you to do that one on your own. Come to class tomorrow with that done. Let's talk about it. Here's a typical regions question here. So volume, temperature, pressure, and looking at it in terms of gases. So they tell you that cylinder A contains 22 grams of CO2. And that cylinder B contains N2. They don't tell you how many grams. They tell you that the two gases are indicated, all their values are indicated. Their volumes are equal, their pressures are equal, their temperatures are equal. First they ask you about the moles of CO2 in container A. That should be a review question from the mole chapter. The second question, 78, asks you, well, why are the numbers of N2 in B the same as the molecules in CO2? So why do they have the same number of molecules? And this is one where we would have P1, V1, N1, T1. And this would be for our N2 right here. And for our CO2, well, it has the same pressure, the same volume, the same number of moles, and the same temperature because all the values are the same. And this is basing, like on our gas law question. Here's our combined gas law. Two different gases, no matter what they are, they will have the same number of moles and the same molecules present as long as their conditions are the same. Think about why that's the case, and we can discuss that also tomorrow. And then 79 here, try this question on your own. They talk about the temperature in CO2. They increase the temperature in that cylinder to 450. They say that the volume stays the same. They want you to calculate the new pressure. So give that a try, see how that goes. Alright, one other thing I want to do with you before we stop for this video is finding the density of a gas at STP. Finding the density of a gas at STP is really quite easy. Remember that density is equal to mass over volume. What you can do is you can assume 1 mole. And by assuming 1 mole of the gas, the mass becomes the gram formula mass, or the molar mass as it's called, and the volume becomes at STP 22.4 liters. And this will equal the density of the gas. For example, if we had something like, chlorine, the gram formula mass is 71 grams, the liters 22.4 liters. If we divide them out, we'll get the density in grams per liter. The only other stuff or substance that we talked about with density was really things like metals, like aluminum we found, the thickness using the density. You'll notice the density of that was grams per milliliter. Gases are, as we have been alluding to, when we draw them in a container, they have very low density because they're spread out. There's lots of space between them. A solid is packed together. Water, another substance that we always talk about the density, 1 gram per milliliter. Grams per milliliter, 1,000 times more dense than the average gas. So what we've gone through in this particular video is we talked about the different laws. You have to memorize their names, know the equations, know the graphs. You have to know what the combined gas laws are. You saw some sample problems. They're pretty straightforward as long as you read them carefully and are aware that STP means standard temperature and pressure, and those are actual values. And we talked about the density of a gas. What we'll do next time is we'll talk about the ideal gas law, PV equals nRT, how to make this all work for us. And you've already seen this just in a different form, and I will explain this to you, and we'll do PV equals nRT, the ideal gas law, and all the things that go along with it. All right, thanks for watching.